Today's problem was submitted by a viewer, and it says, a fair coin is being tossed until the last two tosses results create a combination of either heads or tail heads. Which combination, head or tail head, is more likely to occur, and by how much? Okay, so I've seen a very similar problem to this before, where we're not looking for a combination of two flips, but a combination of three flips. So part of this, the one that's more likely to occur, or the one that's, it's not exactly, in the phrasing of the question, it's not exactly precisely stated what it means by which is more likely to occur, but one possible interpretation is, you keep flipping the coin until you see, for example, two heads in a row, and the number of flips has it's a random variable, so it has an expected value. Or in the other case, you keep on flipping until you see tail head. That has a certain number of flips. You count the total number of flips. That's a random variable, so it also has an expected value. You could ask which one has a smaller expected value, and you can interpret that as being the one that's more likely to occur. So figuring out which of the two of these is more likely to occur, I think should be quite easy using the same argument that I've seen for the three toss case, but quantifying exactly how much might take a little bit more work. Okay, so the way that I've thought about, the way I've tried to explain the intuitive reason for which one comes first, at least in the three toss case, is to look for when you actually fail. So let's consider first the HH case, heads case. So suppose we have a sequence of coin flips. If we flip a tail, nothing happens. We don't start looking for success. If we flip another tail, we don't start looking for success. We just keep going. So suppose we flip heads. Now, if we flip another head here, we have a success, and the total number of flips here would be 4. But if we flip a tail, we've now flipped 4 times, and we have to start all over again. So the next, the next possible success won't be until there are 6 flips. So if you're looking for HH, then if the last, it doesn't matter what you've seen here, if the last flip is a tail, the earliest you could get a success is after 2 more flips. So now let's look at the other case when we're looking for tail head. Okay, so again, let's start with a sequence like this where we start in a failing state. So a failing state on the first flip, if we flip a head, okay, well, we can't possibly win on the next flip. Suppose we flip a head again. Okay, we can't possibly win on the next flip. Now suppose we flip a tail. Okay, we could possibly win on the next flip if we flip a head. But suppose we don't. Suppose we don't win on the next flip and we flip a tail. So we have not succeeded. But you see now we could potentially win or be successful with one more flip. So I'm inclined to say here that the answer is tail head is more likely to occur first, or has certainly the expected number of flips needed until stopping is going to be smaller for tail head. The way that I might try and figure this out, so, N1, let's call this the number of flips until HH, and N2, the number of flips until TH. And what I'd like to compute, I'm going to try and compute the expected value of N1 and the expected value of N2. And this shouldn't be terribly difficult to do. I might have to think a little bit about exactly how to set the problem up, but the reason it's not too difficult is, we basically have I don't know if like a Markov chain model is the best way to figure this out, or maybe just write down, maybe it's easiest to just write down a recursion that each of these two things has to satisfy. Let me think for a second about how I want to set this up. Okay, I think what I've done here is correct. But in order to check my answer before I continue, well, I think what I'll do is I'll continue with the computations to actually solve for what this expected value is. I should be able to get a numerical value out of this pretty easily. And then I'm going to try a couple different things. I'm going to try doing it a slightly different way, which is similar to this, but not exactly the same. And then I may also just try and verify numerically with either a simulation or another method. But I'm going to continue by hand first. But before I do that, let me explain what I've done. So I've asked myself, what are all the possible combinations of the first two flips? Well, there's a chance that I flip head-head, a chance I flip head-tail, a chance I flip tail-head, and a chance I flip tail-tail. Each of these probabilities is 1/4 because it's a fair coin. And then I asked myself, given each of those possibilities for the first two flips, what is the expected number of remaining flips, or what is the expected number of total flips until success? So if the first two flips are both heads, then this random variable n1 is just equal to 2. So there's a 1 in 4 chance that we end immediately on 2. If we flip a head-tail, well, we're back to square one. We have flipped twice, and now by the argument that I had up here, we have to start again. And so the expected number of remaining flips is just equal to the original expected value. So the total number of flips in this state of the universe is going to be 2 plus the expected number of, the unconditional expectation of the number of flips. Let me skip down to this case. This one's also pretty easy. For the same reason, if you flip 2 tails, then again, you have to sort of start the process again, and the number of remaining flips on average is the same as the expected number of flips originally, and so we just have to add 2 to this. Now, if we flip tail heads, there's a 50% chance you end on the next flip. in which case the number of flips was 3. But there's also a 50% chance that you return to this sort of default state of having to start the game again. And so maybe this should be a 3. Yeah, if you flip a head here, you're successful. If you flip a tail, you have to start again. And so this should be a 3. Okay. And so now I have an equation where I can just solve for the expected value of n1. I'm going to just replace that with x. And each of these probabilities can be replaced with a 1 over 4. Okay, so I get that the expected number of flips until we see HH is 6. So here's what I'm going to do for the rest of for this video. I'm going to do the same computation for the other combination of flips for tail H. I'm going to try and set up something like this. And hopefully I get that the expected number is less than 6. And then I'm going to try and do it a little bit of a different way. Essentially what I've done here is I've written down conditional, each of these is a conditional expectation given that the first 2 flips are given. What I'm going to do is write down something else, which is the conditional expectation on 1 flip being given. And I should be able to solve this in a slightly different way and hope that I get the same numbers. Okay, so let's do it now for tail H, tail head. In fact, I think for this one, it's a lot easier to condition on only 1 flip being done. So if my first flip is a tail, if my next flip is a head, if my next flip is a head and I'm successful, that happens with probability 1/2, and the total number of flips would be 2. If my next flip is a tail, then I have to keep flipping. So if my next flip is a tail, I have in total Okay, so let's walk through what I've done for this other case. And hopefully things make sense here. I hope my numerical values are correct. But what I'll do, not on the video, what I'll do is I'll just verify it numerically. And as I edit the video, I'll post something whether I'm correct or not. Okay. So we're trying to compute the expected number of flips until we see tail than head. So we're going to condition on the first flip being either a tail or a head. If the first flip is a tail, then two things can happen. Either we're successful on the next flip, and that happens with a probability of half. So with a probability of half, the total number of flips is going to be 2. But if we flip a tail on the next flip, and that happens with a probability of a half, then if I flip a tail with a probability of a half, then what I've done, so there's the half. What I've done here is I've written down this expression. This 1 corresponds to the fact that we're conditioning on one flip having been finished. And this quantity represents the expected number of flips remaining given that the most recent flip was a tail. And so I've gone ahead and computed that. Does this make sense? Now I'm doubting whether this is correct. Yeah, so I had that incorrect. So condition on the most recent flip being a tail. Suppose R is how many flips are going to remain until success, given that the most recent flip was a tail. Well, there's a 50% chance that you're successful immediately, in which case R is equal to 1. There's a 50% chance you flip another tail, in which case the expected number of remaining flips is 1 plus this expected number of remaining flips, because you're kind of in the same state. So if we solve for this, we get 2. So I do have an error here, because I'd solved earlier, I'd made a mistake and said that this is equal to 1. So that's incorrect. I'll have to go through some of my previous calculations again here. Let me erase all this algebra and think a little bit about whether this is exactly the quantity I want to write in here. Well, this is definitely wrong because I got a number that's less than 2. So what have I done wrong here? Okay, I get a much more reasonable answer this time. I'm quite a bit more confident in this. Wait, what did I get before? 8 over 3. That is greater than 2. What was I thinking? Oh my goodness. So this is... Why am I getting different answers here? I'm actually a little bit more confident doing it this way. I don't know what I've done wrong in one of these approaches, but I've tried to do this computation now by conditioning on the first two coin tosses. So I've just written this now as a conditional expectation. If the first two tosses are tail heads, then we stop immediately. The number of rolls was 2. Number of flips was 2. If the first two tosses are both heads, then the expected oh, this is where I have a mistake. This should be 2 plus the expected number n2. Because we're back now in a state, if we have HH, we haven't even started to see the first successful step in the pattern yet. So we flipped twice and we're still at square one. Okay, so I'm going to go through the algebra again with that plus 2 in there. But let's go through the other two cases first. If I flip head tail or tail tail, I've seen now in each of these cases my successful signal has started, and so these two conditional expectations I'd expect to be the same. So that's how I've written it here. I've just chosen tail tail arbitrarily. Now the total number of expected flips conditional on tail tail is going to be 1 plus the number of flips conditioned on seeing a single tail, right? And so I want to compute that, and well, the total. There's two possible cases. I could again be successful in the next flip and see a head, or I could flip a tail again, in which case I have this sort of recursive relationship. So I solve for this. Condition on the first flip being a tail, the expected number of flips is 3. So now I just need to make sure I carry through this correction to put a plus 2 in there. All right. 4. Is this reasonable? So it's at least 2. That's good. And then given that if I'm not successful on the second flip, yeah, why did I get something completely different up here then? Yeah, I don't want to just spend a huge amount of time in this video going through trying to find errors and corrections and stuff. I'm pretty confident in this one. This is kind of a much easier case because of this argument up here at the very beginning. If you're looking for heads, if you fail by rolling a tail, then you're back at the beginning of the game, basically. And so it's much easier to write down the conditional expectations when you're looking for heads. I'm not sure. I don't know if it's an arithmetic mistake, if I've completely set the problem up incorrectly, or what. Computing this numerically, especially by a simulation, will be very easy. So what I'm going to do is I'm going to say that my two answers are 6 and 4 for now, with tail head will happen earlier than head typically. So this happens after an expected number of rolls of 4, and this happens after an expected number of rolls of 6, or flips, not rolls. But what I'm going to do is I'm going to verify by simulation which of these is correct, if any, and I'll leave some comments to indicate what the overall answer is. I just don't want to spend time going through more computations like this again and trying to figure out where I've made mistakes. So I'll call it an end here. Thanks for watching. Okay, just as I was editing what I've recorded already, I realized I misinterpreted something, and it is a perfectly precise statement on which of these two combinations is more likely to occur. So I was kind of thinking you had two different sequences, one set of flips that stops at head and one set of flips that stops at tail head. But that's not exactly what's being asked. What's being asked is you keep flipping until you see either of these two things. So it's a sequence of flips that will terminate almost surely. And then we're just asking which of the two terminal conditions is the one that caused the termination. So I need to think a little bit about this now. I do still think the answer is going to be it's more likely to finish in tail head. So what I might do something similar to what I'd done earlier and just the probability. Ooh, but hold on. Things are now a little bit more complicated because if I condition on I'm going to go out on a limb here, and I think the answers are probably 1/3 and 2/3. This might be a little bit easier than I'm thinking. So let's suppose the first roll is a head. Okay, so this is something that we're going to condition on the first roll being a head. Okay, so this obviously happens with a probability of half. The first roll is a head. Now let's ask ourselves what can happen. The next roll can be a head, in which case we're successful. That happens with probability 1/2. Or the next roll can be a tail, in which case we can never terminate in this state, right? There's no way now that if we've rolled heads tails, which happens with probability of half, then if the next roll is a head, then we terminate with this state, and if the next roll is a tail, we just continue, and you'll never be able to see two heads in a row because you'll stop. So now I'm thinking the probabilities are 3/4 and 1/4. Okay, so the probability that you end in head-head is 1/4, because if you ever roll a tail, ever, then you can never end in head-head. You will end in tail-head. Right? We can continue this if we condition on the first roll being a tail. Okay, well, if the next roll is a head, we finish. And if the next roll is a tail, well, we can never possibly end in the head-head state. So the probability we end with tail-head is 3/4. Wow. Okay, so this was a lot easier than the question I was trying to solve. It was a nice exercise to go through that work that I did with the expected number of flips it takes to terminate in one of the two cases. And I believe that this interpretation, this work here is exactly, I believe this is what the viewer is actually asking. I don't know why I interpreted this a different way when I read it first. It is a perfectly, I think it's because the version of this problem that I have seen asks which combination has a smaller or greater expected number of flips until it ends. But in that version of the problem, you're only looking for one possible combination to terminate. Your terminal condition is not two possible combinations. It's only one. So I think I had confused the two versions of the problem. Anyway, it's a really cool problem. This version was a little bit more straightforward, as you can see, just arguing, if you condition on the first flip, you can see you'll either end on the next flip or you'll never get back into a state where you can end on double head. The computation I was doing earlier with all these expectations and so on just goes to show that, conditional expectations can be complicated. They don't, always work in the most intuitive way, and setting things up properly with conditional expectations can be difficult. Anyway, I'll try and add some comments to when I edit the video so you can navigate where good parts of this video are to look for if you just want the answer. But thanks for the submission, and thanks for watching.